Okay, so design and safety. Before we jump into it, there is a small warning because I will have some slides and generally they are not nice. So it's been warned. A few words about the speakers. So of course you can see me, but you can also see Andrea. Andrea Stosic, she is electrical engineering manager by Entity Data, and she has over 10 years experience in the design of hyperscale data centers, as a fancy. Also we have a Sertac Seckiner. He is a sales manager from ABB with vast experience in MV applications engineering. And of course there's me. I'm leading the ML power system with also electrical engineering and power system studies for the last 15 years. Not leading, last 15 years experience. So if we go to this, we have to answer one big question: where electricity comes from. I can give you 1, 2, 3 because we didn't do Slido for it. From the socket. And to be honest, this is a real sculpture if you've never seen in Rotterdam, next to the coal power plant. Okay, so if we are here, of course we have to identify a few things before we start further. Yeah? So we need to know what kind of electrical hazards we have, because this is important to question why we are looking at the designing safe system in electrical installations. Of course, I didn't do Slido for it, but I can help you a bit. Of course, we know shock hazard, we know arc flash hazard, we know electrical fires, which is, I would say, a lot of design-related topic. Yeah, I don't know. Well, it's better. Okay. Oh, it's fine. So, electrical fires, electromagnetic field, and last one we have explosion area. Explosion area is a weird thing because it's not exactly related with, let's say, only electricity. Yeah, but very often. So if you know this, can you spot here which one is actually design problem and which one is not? I should make a voting for it. Yeah, both left and right side. This is really design issue. The middle one is just the maintenance problem. You don't want to work in something like this. So what can go wrong? Like, this is very important to question why we are looking at it. Of course, this can go wrong.
Whoa.
When it talks about the arc flash, this was 25,000 amps half-second test only, which is something around 16 to 20 calories per square centimeters, just to give you reference. But it can also end up like recording when you can see something like this. Very minor accident. Actually, it would be sometimes hard to call it accident at some point. There is a bonus if you look this side. Yeah, unexpected things. So the question why we look at it is because when we talk about the arc flash, and we will talk about arc flash today, sorry, shock hazard is a well-known thing. It's not ignored, there's a lot of accidents related with it, but we will talk about the arc flash mainly. And if you look at it, we expect damage to installation. There are things how to solve it, and I can maybe guide you to it, but we expect damage to installations. Different things can happen, different levels, different of voltage, and whatever happens, we expect. We don't expect, we don't want to have this damage to buildings, and there are multiple things. This doesn't have to be arc flash. It can be also electrical fire, a lot of other things that can happen, but just to give you reference, yeah? Oh, no warning, sorry. And injuries. And this is our big why. This is why we look on the safe electrical system. We don't want to have situations like this. And that's because, I will skip it, sorry. And that's because of this, we are focusing on a lot of design-related things. Not only, I would say, so there are hierarchy of controls, I will come back to it, but this is our big why. So what we can do with it, yeah? We can identify the hazard, so the first thing. We can also look on the risk assessment to have a likelihood, so we can assess how likely it is to happen. We can, of course, adjust design in early stage, which is probably the cheapest thing if you can do if you design anything. We can adjust it in the late stage, which is probably more expensive, a very painful process when you are working on project, especially from my perspective. And we can also, because there's a lot of existing installation that we have to handle, so yeah, we still have to work with this. And I will give you Andrea will give you a lot of details how to handle it.
Thank you, Marcin. I think my microphone works.
Yeah.
So, good morning, everyone. I'll be talking about identifying the hazard levels and arc flash risk assessments in general. So where do we start with identifying the hazard levels? Well, clearly, we need to be familiar with the relevant standards and the relevant guides. Perhaps the most important standard would be the NFPA 70E, which is a US standard for electrical safety in workplace. And it's a pretty good standard if you want to understand more about the PPE categories and about safety in electrical operations in general. Further important guide would be the IEEE 1584, which is a guide for performing arc flash studies. And I would say it's equally important for consultants working on arc flash studies and calculations as it is for someone such as myself who works client side but guides the process, reviews the studies, and just works with the consultants as well. You can also see on this slide an example of a Canadian standard, further to US standards, and a German guide for selecting PPE levels. Of course, we know to calculate the incident energy levels, we first need to know the bolted fault currents or the short circuit currents. So we as well need to refer ourselves to the relevant short circuit standards. In Europe and the UK, this would be the IC 60909 and or IC 61363. In North America, these would be the equivalent IEEE standards or ANSI standards. And as always, local regulations, local wiring standards are applicable as well. So on the next two slides, I will basically summarize the arc flash risk assessment process from my experience and break it down in some tangible steps. And hopefully this will help you as well if you're ever in a situation like myself. So how do we start? We start by the most basic and most obvious step. We engaged a skill consultancy. And as obvious as this step may be, it is actually going to set the tone for the rest of your process. So do make sure that you do your due diligence here, that you know that you're working with someone who is knowledgeable, who is up to date with the latest versions of the standard, who just understands these arc flash studies, who is proficient in power system studies, who does this a lot. This will make your life so much easier. So you'll need to agree on the fee, of course, on the scope, level of details, level of engagement, and the IEEE 1584 can really help you here. You'll also need to agree on the deliverables. This would typically be the report and the label, sometimes the model as well. Once you've done this step, the next step would be data collection or data acquisition. So in my case, this step would be completely on me and my colleagues to provide the consultants with the latest and greatest schematics, which of course need to be up to date, with the sequence of operations document, extremely important to provide that. Technical submittals, equipment data sheets. If it's an existing site, a site visit is necessary as well. Then I propose an initial workshop, and this is basically to identify any gaps, to discuss the information shared, to discuss the sequence of operations, make sure that the consultants understand how this site operates, because this will be critical for them to set out operating scenarios in the software that they're using. Then they get started with system modeling, and typically they'll use ETAP or SKM, which are two most well-known software packages that originate from the US, but they're broadly used across the world. Next step would be calculations. So which calculations are required? Well, we will need short circuit calculations, we will need equipment evaluation, potentially power flow study, selectivity study, arc flash study. Once this has been done, I suggest to make this a collaborative step, involve the client and the consultants, get them to come together to the table and discuss the results, discuss the findings, discuss the safety concerns, discuss the recommendations. There's usually a bit of a trade-off between the selectivity and achieving low incident energy levels, so it is important that everyone comes to the table and that everyone understands the final result. So this step may take a few iterations. The consultants may go back, recalculate, do something else, and then once everyone is on the same page, they will go ahead and produce the final report. The final report will include all the operating scenarios, as we mentioned already. It will include the recommended settings. It will have to highlight any sort of safety concerns, and definitely it needs to include the labels. So now that we have the report, the labels, the model, what do we do next? We train our site operations team. This is the team that goes and does electric switching on a daily basis, perhaps, and it's critical that they understand the hazard because they are the ones exposed to the hazard. It's critical that they know how to read the labels and that they understand the importance of wearing appropriate PPE levels. Last but not least would be the site implementation step, basically sticking the right labels to the right switchboards, to the right panel boards. And this would typically be reviewed every 5 years. However, I must make a disclaimer here. If you do have any significant changes in the electrical infrastructure or you make any changes in the protection settings, then you will need to do the reassessment right away. Then you cannot wait for the next periodic review because you could be potentially impacting the incident energy levels significantly and your labels may no longer be valid. So now I'll show you a practical example. This is a picture of one of our switchboards. This is a main low voltage switchboard, 4,000 amp, 400 volts on one of our European sites. This is just one of many switchboards. This is a large and complex existing site. And on the schematic diagram on the right, you can see how the switchboard is represented by a bus bar. What you cannot see on the picture, but you can see on the schematic, is that this switchboard is basically right downstream of a transformer. This is a medium voltage to low voltage transformer. There is a medium voltage relay and a breaker in the upstream medium voltage switchboard. Again, you cannot see it on the picture, but you can see a low voltage circuit breaker, as in the incomer circuit breaker here. On the next slide, I will show you how changing the protection settings can greatly impact the incident energy levels. And in this case, it was for the better, and it was a significant change as well. So here you have the before and the after situation, before using the existing settings that we had implemented on site before we started with the arc flash study. This is a time current characteristic graph. Basically, every line will represent a different protective device. And when we started doing the arc flash study for this site, we calculated actually more than 40 calories per centimeter square on this particular switchboard. To be more precise, it was around 61 calories per centimeter square. This equates to over 4.2 meter of arc flash boundary, and the PPE required is rated over 40 calories, which is not that simple. When we made the protection settings tweaks, and we mainly changed the protection settings of the low voltage incomer and the medium voltage relay, we managed to significantly improve the situation. So now you can see we have a PPE that's rated for 8 calories per centimeter square, and to be precise, the incident energy achieved now was 5.28 calories per centimeter square. And this was a great example, so that's why I want to share it with you and also let you know that this is usually the first step, because this is the simplest step, is the quickest step, is the most cost-efficient step. So we always start like this. There will be cases where we will change protection settings and perhaps won't achieve the targeted PPE level, but then there are some alternative steps that you can take, and Marcin will talk you through later as well. So on this slide, I'll just like to show you PPE categories as they're listed by the NFPA 70E if you're referring to the table method. Companies like Scanware would also display the categories in a similar fashion. And if we compare the PPE category 2, which is an 8-calorie suit, which we just discussed, to, for example, category 4, which is 40-calorie suit, we can see that the 40-calorie suit is significantly more serious. Later on, when you do go out for the break, check the gloves that Scanware team has on display. When you look at the 40 calories gloves, you will see that the glove is really thick. like you have a good flexibility and you have good movement, but your fingers do not feel as accurate as normally. And it's just important to always try to reduce the incident energy levels as much as we can, because generally the feedback from the operations team when they have to wear a 40-calorie suit is not great. It's not comfortable, they sweat a lot, they just don't like wearing it. So if we can reduce this, we definitely should. This is not to say that, for example, if the incident energy level achieved is somewhere between 25 and 40 calories per centimeter squared, that operators shouldn't wear it because it's difficult to wear. I definitely do not support that opinion. I think it's completely wrong. It doesn't matter if the task takes 2 minutes, 50 minutes, whatever. If that's the PP level required by the label, then the operator needs to wear it. However, if by using design we can reduce it, say from category 4 to category 2, then it just makes life a lot easier for everyone. And my final slide, I just wanted to show you some examples of arc flash labels. They're typically pretty similar. Here you have an example of 2 labels in English and 1 label in German. There's not a prescribed look, however, they all seem to follow a very similar look, and they will all pretty much show you the maximum incident energy, the arc flash boundary, working distance, voltage level, and in NTT we also show restricted approach, limited approach. And if you take a closer look, there is a small disclaimer that we put in NTT as well, and this is just to say if you do make any protection settings, reassess the situation instantly. The labor may no longer be valid. Thank you.
Okay, I'm back to the microphone. So, what we can do about the design now? So, Andrea precisely explained how we can calculate, but from our perspective, yeah, of course, we do comprehensive check. That was this part. We do review actual status, yeah, and issues. So this is part of the site visit, to be honest, but also outcome of the studies. This is very important, cost versus effect. Because unless someone is really in the fancy place where you can spend a lot of money to improve something, 1%, most of the companies are not in this place, so they have to choose wisely. We are setting up practical goals, which means really practical. I can tell you unpractical goal, for example, is reduce the transformer to 5.7%. This is very unpractical because you don't have a control on how to short circuit impedance comes up after the test. And we, of course, look for the local regulation. This is just not to violate something locally, because sometimes local regulations are actually strict, and they are good. And, of course, we go above minimum requirements. So just to give you some, we will not talk about it, there are some standards related with the arc flash or electrical arc, let's say, how we can implement it in our electrical systems. Some of them are quite new. It's just good to know, you'll get it later, yeah? If we look from the hierarchy of control perspective, which is in NFPA 70, very nice concept, ISO guide has very similar but just less steps. We will focus from the design perspective on the first 3. Andrea explained identification, and we have also elimination, reduction, and engineering controls. Engineering controls is very interesting topic, very wide area, and that's the problem. That's exactly what Andrea said, that you need to have a skilled consultant that will guide you and help you what to choose. Because there are a lot of options that you can choose already on the market. Of course, settings, the first thing, yeah, the cheapest thing that we can do. But we can also install arc flash relays or arc flash optic detection, depends how we call it. We have also arc flash quenching systems. It's not new, you will hear it about later probably. Well, we can play about the short circuit current reduction, which is a very tricky topic, to be honest. Of course, design, medium voltage, low voltage. Actually, Sertac will talk about it later a bit. But medium voltage, low voltage arc flash, let's say design, which is a very nice thing to have. Adaptive settings, very rare to see, actually. But very interesting thing, current limiting fuses. Generally, most current fuses are current limiting, which is not a rule of thumb, but very interesting thing to have. Zone selective interlocks. Communication, this is communication-based protection. Very useful thing when you run out of the time for protection coordination. ARMS, which is energy reduction maintenance switch, arc flash reduction maintenance switch, very useful things from the maintenance perspective. And we can do it also as a logical thing on the medium voltage relays as well, if you know what you are doing. Differential protection, good things to have. IS limiter, which is product thing. I will not say what company, but it's a very interesting thing to have sometimes. Of course, from the design, from the engineering perspective, IP level, which sounds like the stupid thing, yeah? But IP level is very important from operation and maintenance perspective. If you have it wrong, there will be constant hazard in your electrical system, which is actually a lot of violations that will pop up on the site. Switchgear separation forms, again, the same thing. If someone doesn't really think about it at the very beginning on the design, later it's very hard to change it. Switchgear temperature monitoring, like the fixed one. It's interesting thing that is coming probably from years now, but it's not very common to have. Absence, exactly fixed absence of voltage tester. Probably you will see it on like medium voltage systems as a default, but on low voltage it's not really default thing. Very nice to have. Lockout tagout, I mean not lockout tagout as a procedure, but you need to have a device that allows for lockout tagout, yeah? So you don't have to think around. Yeah, people are creative, but not that sometimes as does much. Proper tools I can skip as a good example, and also like things which are kind of mixed. SCADA system for remote operation. I can tell you where it doesn't work. It doesn't work where you put the panel operator next to the breaker. Then it's very bad design. I would say you can sometimes design things as a new, but unsafe by design. Motor operator breaks is of course linked to the SCADA, and then project design improvement, which is a very nice word for everything we said now. And I think the all details I would transfer to Sertac. Seckiner, he will tell you exactly how it looks like from his perspective.
Thank you very much.
This is mine.
How's my voice? Sounds good. First of all, I have to say that it's great to see all you are wearing your ABB lanyards. It sounds like an internal event rather than a serious conference. So yeah, we will be talking about the arc flash protection for switchgear and how to design it. So we need to first of all look at the different type of the approaches, what kind of solutions we can do for arc flashes. Obviously, the first and foremost, the passive one, which is basically the switchgear itself. As you can imagine, either low voltage or medium voltage, it's basically metal cabinet that holds the circuit breakers and all the other switching equipment. So we need to comply with some certain standards to be able to build very, very sturdy equipment so that it will keep our equipment itself and the personnel safe. But on top of that, we could talk about the active solutions, which will be constantly monitoring the electrical, the system, the current flow or an existence of an arc during a fault, etc. So to clear the fault as soon as possible before it actually have an impact on the equipment itself and on the stuff. And then lastly, the preventive protection is quite important. It's like monitoring your asset like it's in Big Brother context. So you know whether it has the proper aging, what about the contacts, what about the determinations, the thermal levels, etc. All these things can give you a lot of information about the health of your switchgear, and then you can use these information to prevent a potential occurrence of an arc flash. So we need to understand our environment first. Obviously, on the left-hand side, as you can see, we have the beginning of the switchgear from the high voltage after it is being generated and transmitted to a distribution level station. We have the high voltage to medium voltage substation where our very first switchgear sits. Then we've got the intermediary part, the medium voltage distribution level or medium voltage to low voltage side. And then eventually we get the electric into our houses in the lowest possible level. So all these different parts of the electricity network system needs different kind of designations. Starting from the passive solutions, we need to, as I mentioned, build our switchgear very sturdy. So we need to to comply with the regulations and the standards. And we need to always, as Marcin mentioned, we need to always exceed the minimum requirements. And in ABB switchgear, for example, we always strive to exceed it. And in the low voltage, we have half second withstand capability, and in the medium voltage, it's even higher, because obviously in medium voltage, we've got higher energy levels, 1 second withstand levels. And then on top of that, in the design, we need to take into account several different approaches. At least one of those you see on the slides. But you can either use a preferential path to basically dispose the gases or the arc flash, or you can use arc quenching systems, or you can use different zonal protection. You can have segmentization in the switchgear, or well, in the end, you can also use GIS, so gas insulated switchgear, which will suppress any potential arc flash to prevent and avoid any potential impact to staff and the equipment. In the active solutions, we need to talk about the thermal energy, which will be affecting the equipment and the personnel. Obviously, the impact you will receive from an arc flash occurrence directly depends on the duration of the exposure. So if you touch a lava fluid, just a half millisecond or something, it will not burn your hand, but if you keep your hand longer than that, then the thermal transmission from the lava to your hand will burn your hand. So it's the same. So if you can just reduce the amount of time that the arc flash occurs, or ideally preventing it, but if it happens, you need to just suppress it to the minimum duration so that the impact of it will be minimum as well. To be able to do that, we've got different detection systems. In low voltage, obviously, we use arc flash direct detectors, which will be detecting the arc as soon as it occurs and then send it to the switch equipment to instantaneously clear the fault. That also depends on the speed of the circuit breaker, obviously. Then also we can combine it with an arc quenching system, which just extinguishes the arc internally in the system itself. So those are the potential approaches we can take for the low voltage side, but when it comes to the medium voltage, it becomes a little bit more comprehensive, more complicated, and then you need to utilize several different types of protections. The good thing is here, because we've mentioned about the cost and effectiveness, now we don't have really an excuse not to use arc flash protection, because in most of the protection manufacturer relays today, there is integrated arc flash protection, which doesn't really add up to the cost much, any significance. So you can always include the protection relays and the arc flash protection at the same time to save lives. So there's really no excuse about the cost of an arc flash protection implementation. And also, we just, because we are racing with the time, we have to consider the protection combined with the communication-based systems, because when we use hard wiring as we do in the old school, it is definitely slower than the communication-based systems. And communication-based systems create zonal protection, which will enable the maximum protection and also keeping the unfaulty side of the system alive, which means we are saving the lives, but at the same time we keep the energy flowing as much as we can at the same time. And then lastly, the preventive actions. We can monitor our switchgear. The condition monitoring can be implemented. The thermal level monitoring can be implemented in the switchgear, which will tell us the status of the switchgear instantaneously, which means you can continuously monitor your system and understand whether it is aging, whether it will require any actions in the due course, or whether it is susceptible to any potential arc flash or any other kind of fault due to the aging system. So, in conclusion, design starts from the very beginning And obviously you need to consider the switchgear itself initially, how robust and sturdy it will be, but then on top of that you can include the intelligent devices, which are now not that much expensive, I mean, compared to the lives that can be saved. Right, thank you very much.
So, I don't know why it's not playing. It was a very nice gift for you. Sorry. So, I will give you an example how we did this recently in the last project on our customer side. So, we did just to wrap it up what we told you. Yeah? So I did site audit. We find a lot of issues. We did data collection for the process. We did all the calculations and a bit more that were necessary. We did some initial recommendations. Then, it's a long story short, but we came up with the customer that, based on numbers, that the best idea is to actually replace the main switchgear, low voltage. And we did some what-if scenarios before we replace it. That was the early phase, the cheaper one, considering replacement of the switchgear. And at the end, we did all calculations update as the commissioning phase after they actually install it. Because there were some changes, apparently, as far as I hit the site. What was the situation? I hope you can see it, but I try to point it out. If you look at this, that was the real case on site. From when you enter, you actually can touch the main bus bar from the transformer, which is not a good thing. And also, we end up having lot of selectivity issues, a lot of protection problems. Arc flash energy and the main comer and the switchgear was actually above 55 calories per square centimeter, so quite a lot. And at the end, also there was some shock hazard issues. What we did, we proposed, but this was actually coming from the customer after our consulting. We proposed that probably it's good to replace the switchgear, but just not replace it one-to-one, because it would be a waste of money. We did some calculations. We just find out what we can do. We actually couldn't make it with the protection settings. So we proposed initially arc flash protection, but they also said, okay, let's go with arc flash quenching. Because this site was fully, actually, surprisingly below 1.2 calories at the end, which is unusual, actually, to see. But with this medium voltage, this low voltage switchgear was main issue. So we actually improved selectivity, still have a medium voltage problem because they have a fuses, so yeah, there's nothing I can do at this moment with it. And we end up with having arc flash energy below 1.2, not above, below 1.2 calories per square centimeters on the whole low voltage switchgear. And this is thanks to this arc quenching system, which you will hear later what it is, actually. And if you look at it from side to side, there is no big difference from outside, yeah? If someone doesn't really know what's happening, who just went, it's like almost the same. But there is big difference inside, and there is big difference how it works. And because of the arc quenching system, before we also have a communication between low voltage and medium voltage breakers, so we can intent trip it. We could be able to reduce everything significantly. And this is one of two sites I have, which we actually went whole site below 1.2 except medium voltage, which is quite nice for them, actually. So what next? Of course, you need to design it in details. You need to purchase the system. You need to build it and implement it. All phases are apparently critical because there might be differences between this. And at the end, you have to commission it, which is the topic for the next speakers. And we have now time for Q&A session. And I think we have to go to Slido, yeah? Yeah. Okay, let me read it. Okay, there's a lot of questions. So we try to mandate level 2 PPE as a minimum and have lots of pushbacks from directly, I don't know what this is. I cannot read it. Staff and contractors, how do you suggest we overcome this? By the electrical safety plan. Yeah, I simply can say it. He's here. Okay, that's for you, Andrea.
Sorry, I don't think I really could catch the question well.
No, the question was if we can mandate 8 calories as a minimum. Yes, you can, but you do it in electrical safety plan that you have to do it for your site and or for your organization. That's it, if we don't want to go into too much details at this point. Do you think an arc flash study is worth circa 100,000 euro only to give PPE requirements? What other value does it bring? That's for you.
The arc flash study cost depends on the complexity and the size of the site. Obviously, it's not always going to be this price. When you think about how would you put a price on someone's life then, right? What would that price be if someone goes and does the switching and is not prepared for the level of danger that can, thank you, that can come out? Then what's the price there if we lose someone's life because we didn't want to spend 100K or whatever, many thousands for just to save costs? I don't see that.
Well, I can add, it's not output, and Andrea said it in the very beginning. Arc flash study is not only PPE level, it's selective video equipment evaluation, short circuit, and arc flash, and sometimes even power flow if you need it. So this is complex study of few things. It can be super simple, but
power system study, exactly, yes.
Okay. Mindful of regulation 14 of the electrical at work regulation, avoidance of live working. Is arc flash protection more for equipment protection opposed to protection of persons? I think Sertac, you can say that, yeah?
Well, equally. No, it's not just for the equipment, because when you implement the arc flash protection, it reduces the clearance time to a very, very low level. Obviously, that depends on the circuit breaker opening times as well, but you can get like 60, 70 milliseconds of clearance times, which is compared to just relying on the grading study, which can give you like 400 or 500 milliseconds of clearance time just based on the overcurrent protection. That gives you a great safety margin for your personnel as well, not just for the equipment. So it's not only, I can't say it's only for equipment, it's both at the same time.
And I think I have one more for you, Sertac. How does GIS and cabinetry or enclosures affect the incident level provided?
Well, I don't have the numbers in calorie per centimeter square, but obviously with the GIS, the ideal expectation is having no arc flash, because that will be expressed inside the cabinet and it's not going to affect any external equipment or the personnel. So, but in normal switchgear, obviously I don't have any numbers for that one, to be honest. But again, going back to the arc flash itself, the protection is quite important. With an AIS switchgear, whether a low voltage or medium voltage, your clearance time is probably more important than the energy emitted by that flash itself, because of the exposure times is the most important and critical property for this.
Yeah, and if I can add comment, there is no effect of cabinet. Well, there is, but technically you don't consider it closed doors, open doors, if you mean something like this, officially in the calculations. And from GIS level, it depends if it's fully GIS or it's like small part of the like breaker is GIS, yeah? So that makes a difference as well. Okay, it's going too fast, yeah? You have to slow down. I think we have 2 more questions and we have to go on, yeah? Because it's about the time. Yeah? Ah, okay. Let's go. So, why the arc quenching system is not fitted as a standard? There will be more, guys, like I can say that. There will be more about the arc quenching system later, but there is a standard for it. There is a standard how to implement it. It's just, because it's a bit of, I would say, more expensive thing, not fully expensive, I'll not call it this way. It's just, no one will force you to do something like that, yeah? There is a minimum requirements in standards, not maximum. Slow down. Okay, Andrea, this is good for you. How would you account for likelihood as a part of overall risk assessment in your approach to arc flash?
I feel like this is a better question for you because you're the designer, but
yeah, but I think you can say it. Yeah?
I think I would start with what the construction of the equipment is, right? And there are some standards for medium voltage equipment, as Sertac mentioned. Low voltage equipment, there's a technical guide. So you can start by assessing what infrastructure you have in place. Obviously, there are some tables for the likelihood of the event. I think you should add to that.
Well, if I can add, it's like you can build your own system for it. It depends really what's your goal. What is your practical goal? If you would like to find out if this is old switchgear, is it exposed, not exposed, technically, because it's a subjective thing. I have people that can open fully exposed switchgear without anything, and they just don't hesitate doing this. And some people will just say, yeah, we stay 4 meters away. So it's really subjective thing, but and there are no standards to it, unfortunately. So it's per consultant. But the risk assessment, if I can give you a hint, the risk assessment is really part of permit to work. We try not to do it during the arc flash study because it's for today. And tomorrow it can change, yeah? Someone can hit it with forklift or something. And in my report will say low risk. And eventually next day it might be super high risk, yeah? Because it was flooding or something. There's a lot of questions to you, Andrea. Andrea, what settings did you change or adjusted to achieve the reduction of incident energy in your example?
Mostly the changes were within the instantaneous region of operation. That will typically give you the instant gratification, so to speak. We changed the low voltage circuit breaker, we changed the medium voltage relay settings as well. I don't know the exact numbers now to the top of my head, but it was basically, we tried to make the protection more sensitive, so it tripped faster and at a lower set point than what it did originally.
Do you have an arc flash study for DC batteries?
Oh yeah,
Yeah.
it's a similar question. Just I want to know what is PP level usually for UPS batteries? What is the typical expectation? How much energy is, so that kind of things I would like to know. Thanks.
It depends. If you have 2 megawatts hours battery, 5 megawatts hours battery, or 10 kV, it's like kilowatts, yeah? It really depends on the system, and it depends how it's connected. And for example, if you look on the new UPS design, they sometimes have a middle fuse in between the sections of the batteries, which will make it better. Yeah, so there's a lot of things to consider. I don't want to say what is the default thing, because the default probably will everyone send 8 calories, but it depends on the place of the battery. And you also have to look on the UPS itself. It's super packed, so if you open sometimes enclosure, you have AC, DC, and linked to the batteries, and everything is in one enclosure. And actually your DC might not be a problem, but your AC side, which is still 20 centimeters away. So it really depends.
Is it, can we validate that through the power system studies, or I need manufacturer data for assessing?
It will be, depends on the site. For the DC, you can do it actually as a manufacturer by default. Technically, it's possible. For the rest of the UPS, it will be system, because you have to connect it to something. And this will make a major issue, major impact on it, on the results.
Okay, thanks.
Okay, what's happening here? Okay, can I skip British standards? I know they are not clear, and there's not, recent upgrades are not even making it easier. Okay, something to you, Sertac. Question for ABB. So all of us. Many of the safety attributes you mentioned are optional extras. How can we change the industry mindset to ensure these options are used?
Very valid question, I must admit, but equally, I think there is not that much resistance anymore it used to have. Because, first of all, they're not really optional extras anymore, at least most of them, like the integrated arc flash, which are coming in the relay as a part of the relay. And we're combining another question, if the ABB switchgear has arc flash retrofitting options or the plans. We also have a standalone arc flash system, which is comparably cheap. It's not really super duper expensive. So convincing end customers, consultants, integrators, even the contractors is much easier now to implement the arc flash. So I appreciate that that's a concern still, but not as much as it used to be. And obviously doing it further is just mentioning about the benefits, showing the videos like Marcin showed. I mean, I've got another video in my computer which is showing the a medium voltage switchgear explosion and another comparison video showing what happens if we implement an arc flash protection to the exactly same switchgear and how much it doesn't explode, actually. So all these things, we need to just convince each other, basically, because we are this much. So we just need to convince each other.
Yeah, there is one simple. Why is incident energy expressed in calories per square centimeters? It doesn't have to, it can be in joules. Actually, in DJUV it's in kilojoules, so it's just energy. I think calories per square centimeter is popular because when you buy PPE, you actually refer calories per square centimeters because companies like Seckiner, they really like this one because it's a round number like 8, 25, 40, which is easier to work with, yeah. If you want to know how joules is 4 times 184 times calories, so that's it. And I think the last one, because it's interesting one, I think I will address it, yeah.
Sorry, what we're just looking at. As we're going through on the polls as well, we're seeing a lot of questions coming through. And I just wanted to pick up on some of the popular ones and throw them out to the panel there
okay,
as well.
if you have it, yeah.
Okay, British standards. We all talk about, and Andrea, you mentioned them all. You brought up all the different American standards, Canadian standards, international standards. Where are we with British standards? What's the challenge? Why aren't we taking arc flash into British standards and adopting it?
Well, I can tell you one thing. You have it. The thing is that you have it, but you look on from the, not from equipment perspective, but you have to look in the BSEN 5010. Because it is there. There is Annex B6, whole about arc flash. And I think there is new 2023 or 2024 version of it. So it's not that you don't have it. You actually have this requirement. That was the previous question. Is it really like, I would not like legally required. You got biggest fines in Europe, like mainland, yeah. Like you got this, you are still in Europe, yeah. Maybe not in European, but in Europe still. Okay. So it
We're
is
playing
there.
Football there. We'll do that.
Yeah.
Ish, or they'll do the ish bit.
So you have it, yeah.
Okay. Another one then. Sertac, I think this was one more for you. Could the OEM do an arc flash risk assessment on their equipment before it's put it on the market?
Well, is it for me? But I don't know. But yeah, they can do, absolutely. Yeah, well, there are obviously test laboratories that they can just take the switchgear to the accredited laboratories and they can get tested and approved if they are valid. Yeah. Then they can fit their switchgear with manufacturers' arc flash protection gadgets as well.
Yeah, and I think that's the challenge, isn't it? Looking at arc flash, it's when you're putting switchgear in, it's the system it's connected to as well. When you're looking at it from a manufacturer, you're looking at what it can withstand or the short circuit capability on there and your short circuit device. There's one question came in about that shorting device. Okay, how much does that cost? And I'm going to add my little bit. Can it be retrofitted to existing equipment?
It can be retrofitted. Well, we don't call it as arc quenching system in our system, in ABB medium voltage, we call it UFES. It's like an earth switch, which basically gets conductive when there's a high energy levels and a high voltage situation. So it's not the cheapest chip, I must admit, but it can be retrofitted, and comparing the potential of that device to save lives and to save the equipment itself, obviously it's not even comparable to in terms of costing. Yeah.
Absolutely.
But it is retrofitable, absolutely.
Yeah. Okay. Another one that's equipment, so I'm sorry you might get one or two on here.
Sure.
Okay. Lotto. We talked about Lotto, looking at the equipment. Realistically, that should be a primary focus for what we're doing when we work on electrical equipment. How do we ensure that that is an absolute requirement for that equipment before it leaves the factory? It should be in the standards, it should be there, and it should be fitted.
Well, there are two aspects of it. The first one is the mechanical interlocking, which should be by the design of the switchgear itself, a mechanical interlocking, such as not being able to open the switchgear doors while it's energized, or if the circuit breaker is in service position, you won't be able to do any labors to the switchgear itself. That's the first part of it, and it is, well, for ABB that's default, and it has to be default for any other manufacturer as well, which I believe it is anyway. On top of that, you also need to, because there is always a way to trick the mechanical interlocking. So obviously we are relying on people, and when there is tight times, that you need to do very quick actions and you have a pressure from management or somewhere, people might try to kind of trick the mechanical interlocking, which is kind of possible, unfortunately. So you can always consider adding electrical interlocking, which used to be based on the hard wiring, but now we can implement PLC functionalities to the intelligent devices we deploy to the switchgear, which actually gives me confidence about, because usually we are not educating that deep to the people who are operating the switchgear to manipulate the protection relays by their configuration, which will disable them or prevent them to do any kind of trick with the interlocking, which means by electrical interlocking and the intelligent devices, you can ensure the lot are being implemented at all times without any compromise.
Exactly. And that is that challenge of actually how you actually train everybody up on that, on around arc flash. Unfortunately, as engineers, we suddenly become experts on this, and Andrea, you've done an awful lot of work in that one. But it's training that team, and how do we get that message down to the team to ensure complacency doesn't kick in. You know, there was a challenge there you mentioned earlier about asking people who are around wearing arc flash PPE. How do you get that message across to your teams to ensure people do wear the appropriate PPE and understand the importance of that?
I would say you buy PPE. Yeah, that's the first step, yeah?
Exactly, you know.
And you force them to wear it.
Sorry?
Following on from that topic, why can we not do really tangible improvements to ensure that people aren't inside the enclosure to verify the state of the enclosure? So things like designated test points outside of the enclosure for points of verification, things like that, aren't expensive solutions, but they keep people out of the environment in the first place. They can guarantee that there's no energy present from outside the enclosure. So why not just do that? It's an engineering solution that circumvents loads of this requirement.
We do. It's getting more often. It's just a matter of standards and tests. What we call absence of voltage tester in Europe, or voltage detector. There are two standards for it, and this is misleading a bit for people. But this is coming. Yeah, it's getting more often in the enclosures by default already.
Okay. There's a couple of different questions that came up around car charging, and electric car charging, superchargers. How do they affect an arc flash calculations? Because clearly your sources will change from time to time. What's plugged in, what's actually part of that, and what's their contribution to the system? Have you looked at something like that?
I did, but I
effectively
know.
comes
Do
with
you want
battery
to?
systems as well, doesn't it? So data centers and that side.
Okay, so there are two things here. One is about the battery charger, which can go up to 1 megawatt now, peak charging, and also the, let's say, EV or car or truck, whatever is connected to it. The truck itself and the charger is communicating, so there are systems in IEC that is saying how you have to disconnect and has to be safe for people operating. Because this is like the fuel pump, yeah? I actually can use it. We have this discussion recently on one of the assembly line for the automotive cars. And technically, from the calculation perspective, it will not be very high energy, or it might not be very high energy. It depends, again, on the system. But the difference is if you look from the AC or DC side, or how big the truck is, yeah? Because then if you go deeper and deeper and around the battery, this is like the question that I've seen here about the EV cars. That, for example, if you have a car mechanics now, people servicing the cars, they kind of probably didn't catch that they are now electromechanical guys now. They are not mechanical anymore. And they also need some PPE and training for it as well. And there is some energy and there is some risk related with it, but it requires a bit more education and process, to be honest.
Okay, I'm going to ask one final question. And this isn't for the audience, isn't for the panel. Okay, so this is more for the audience that's come in. So as the questions come in is how many people or how many companies have actually carried an arc flash study? Is that something that's regular out there? It's a good show of hands out there, isn't it? At least 50% out there. Okay.
That's good.
Good. I'm hoping by the end of these 2 days, that figure's going to start changing, because people will be going away from this thinking, maybe that's something we need to include in our safety systems.
And
Okay.
I can say if you can catch us later if you have
Yep.
more detailed questions, of course.
Okay. Thank you,
Thank you
everybody.
very much.
Okay. Thank you, everybody, on that one. Now, it's the second most important time of the day. Okay. Oh, sorry, did we have another question? I hope we didn't, because I've been left stood up on the stage by myself, but go for it.
At a construction commissioning stage, so we come in, and I've found a lot that the arc flash studies that get presented to us are wrong. Not on the, it goes too far the other way. So when we check it ourselves and we do our own calculations,
Yep.
and we are having the discussion with our clients to go, no, this is wrong. So the cal rating for that piece of switchgear will say 250 cal.
Right.
That means I'd have to wear 5 bomb suits to operate that are proved dead on that system.
Exactly.
And going by my safety policies and standards, we have to wear the appropriate PPE.
Yep.
To even prove dead on a system, to prove it dead. How can I even do that within the arc flash boundary of a 250 cal rate? And when we've done our own calculation, and the actual trip times is, you know, it's instantaneous. So it brings us back down to 16 cal.
Yep.
So we can wear suitable PPE and change it. Is there a sort of accreditation that I can take for myself to say the protection changes? On a commissioning site, we can change the protection settings 6 times by the time I finish the program. Is there something that I could use to say, no, I'm not using your arc flash study, this is what we're using, and this is how I've done my own calculations, and is there a course or accreditation that we can get as a company to say, we do our own?
I think that would be a very difficult accreditation for doing something like that, but I think that's really where you need to work with your client and your customers to work through the different stages, because and we'll have sections through on commissioning as we go through these 2 days, and it's understanding through that commissioning sections that as plant comes online, it will change, okay, and the risks will change, but you've also got to look about what activities you're doing as well in there as where that risk comes in, okay, and it's understanding that. I don't think there's a one size or one tick that says, yes, you're good to go and you can do that. I think it really is down to that communication between all parties to agree those commissioning stages and how you manage that and how you manage it safely. Okay? Yeah. All right. Okay, thank you. Sorry.